This is lecture 6, part 1. I'm going to start working towards mass spectrometry at this point, but to get to mass spectrometry, I have to describe some early experiments, namely the behavior of cathode ray tubes and the glow discharge. So historically, the glow discharge is a high voltage phenomenon. It involves the ionization of gases and glass. And the natural version of this is the so-called St. Elmo's fire, when you have a thunderstorm nearby and objects, which act as an anode basically, start to glow, and because of the ionized gases in the atmosphere. So we start with the basic gas tube. So I'm going to illustrate it as a tube with two electrodes inserted in it. I'm not showing, but the tube is generally attached to a vacuum line and a gas supply so that you can control the gas and the pressure within the tube. In terms of a circuit, you hook it up as follows. So you have a high voltage power supply, a voltmeter that goes up to thousands of volts, and an ammeter, which determines the current through the tube. So I have omitted a potentiometer voltage divider that would ordinarily be used to control the voltage in the tube. In one type of experiment, you determine the voltage at which a spark develops in the tube, and you can plot or determine the onset of the sparking as a function of the gas pressure within the tube. So that becomes one piece of information. One finds similarly that at a given pressure, if you move the electrode or change the electrode distance, you find that the spark voltage decreases. So there are going to be two pieces of information from a sparking experiment or a gas tube experiment. And specifically, those two parameters are the gas pressure and the distance between the electrodes. It's found that the product of those two numbers becomes a determinant factor of the threshold voltage at which you have a spark develop in the tube. The data are presented as a so-called Paschen curve. So the pressure multiplied by the distance between the electrode is the x-axis. The voltage at which you see the onset of sparking within the tube is the y-axis. There is a minimum value that is the optimum sparking potential or parameters for the tube. What you see in the tube depends on the combination of the pressure, and this is for a fixed interelectrode distance, so it's around 50 centimeters for this experimental tube. So at atmospheric pressure, you require a great deal of voltage to cause electrical breakdown, and as a result you get a very narrow filament, very bright, to spark through the gas. As you decrease the pressure in the tube, the onset of sparking is markedly decreased. Notice that it's around 10 kilovolts. This is the second tube from the top. And the band, the ribbon of discharge, starts to broaden and become somewhat diffuse. As you continue to lower the pressure of the gas in the tube, you broaden the ribbon further, and you start to see structure in the discharge itself. There are names for these different discharges, but they're primarily used as descriptive terms. There's some phenomenological basis for them, namely what occurs, what are called space charge effects, as the formation of ions causes gaps in the space. We're not going to go into this in detail for this course, but just notice that the pressure differential and the onset of the voltage. If you really pump down on the tube, this is the final illustration at the bottom, so go to extremely low pressures, there's nothing in there, you basically made an insulator, and you raise the voltage to extremely high values, namely the 100 kilovolts again, you start to see the tube itself, the glass, starts to fluoresce. So the gas does not glow, the glass starts to glow as a result. So the glow discharge is very pretty. I want to get to a more practical matter now, namely the cathode ray tube. And so it's a similar design. Well, it is the same design. The electrodes tend to be closer together, and so you're not working with such high voltages as a result. The gas, the tube is pumped out pretty much completely, and you see a beam appear. The beam consists of something that's passing between the electrodes. There's current flowing, so they're clearly charged particles of some sort. Question is, what are they? And we're going to do some experiments or describe some early experiments that worked out the nature of the particles or the things in the beam. So one of the things we can do is modify the cathode ray tube itself, move the electrode off axis. So this would be the anode in this particular case. And the wall of the tube is coated with zinc sulfide, which renders it fluorescent. So you make a fluorescent screen. We're making a TV tube, an old TV tube, or a cathode, or an oscilloscope tube if you want to come down to that. So the cathode rays are emitted from the cathode. They travel through space, and because the anode is moved off axis, they continue through space a lot like the Wile E. Coyote keeps going off the cliff when he misses the roadrunner and before gravity takes hold. So the beam smashes into the fluorescent screen. You see a very intense light spot where the cathode rays strike. We'll talk about the focusing shortly, but this is the observation. If you have a glass blower who has facility, you can also insert electrodes into the walls of the cathode ray tube that are perpendicular, arranged perpendicular to the beam, and thereby set up an electric field across those electrodes in the middle. And by applying a voltage across those electrodes, you can bend the beam either up or down depending on the polarity of the electric field. So this tells you that you are, in fact, or confirms that you're dealing with charged particles. The fact that you see a current tells you that they are charged particles, but more importantly, the fact that you can deflect them tells you that they are charged particles that have a particular mass. Similarly, you can put the cathode ray tube between the poles of a magnet and likewise deflect the beam. So here's a photograph of one of those cathode ray tubes from a Sotheby's catalog, I believe, or Christie's catalog, I can't remember which, selling old scientific antiques. So this is another type of experiment, more whimsical in nature. So you can see the fluorescence on the screen. The beam is not particularly well focused here, so I kind of exaggerated the beam's, shall we say, spot being precise in the previous slides. You can focus them. We'll talk about that in part 2. But this is one of the early experiments. So you put an object in the path of the cathode rays, and you cast a shadow on the fluorescent screen opposite, which shows that you are actually intercepting particles as they are emitted from the cathode. You'll note the shape of the target, namely an iron cross. If you're familiar with Weimar Germany, you'll realize that this is a shameless attempt to get grant money, in the sense that these are German scientists who want to appeal to the militaristic nature of their government. So they put the iron cross in the tube as a target. The British, who are a little more whimsical in nature, there is an experiment, I could not find a picture of the tube, but they put a little water wheel type device in the path of the beam, and the beam, by striking it, turned the water wheel like device. But the point is that these experiments demonstrate demonstrate that the cathode rays are actually particles. They're not light being emitted, strictly speaking. Similarly, the cathode rays can strike an object painted with a fluorescent dye and cause that dye to glow. So this is another whimsical type of demonstration experiment for demonstration purposes and to get the crowds in to listen to your lecture. So the flowers in this tube have been painted with the dye various colors that when they fluoresce, they give you the colors indicated. When the tube is actually turned off, those flowers, those little sculptures in there look like lead. They're completely colorless. So the upshot of all of this, the cathode rays are corpuscular, which is an old term meaning that they are particulate in nature. They bear a negative charge, and that's determined from the deflection experiments and the direction the beam is deflected in relationship to the orientation of the electric field. And then finally, that deflection in either the electric or the magnetic field, designated as E or H respectively, gives you the mass to charge ratio. So the radius of the deflection is what's used to calculate the mass to charge ratio. And ultimately, we're going to use this in mass spectrometry.